All right, let me start. This is the last slide from last time. I'm not going to go back over it. It's got these 6 questions. But we're shifting tonight away from astronomy for 5 weeks. The 11th week of the course will come back to astronomy. And what's really important for you to have gotten out of the first 5 weeks on astronomy, what's really important is you understand these 6 questions. But that requires a little bit of comment because the field of arithmetic logic is underdeveloped, and it turns out that it probably isn't even perfectly logic. Collingwood is the one person to write significantly about questions, and he's the one who introduced what's called he called the give rise to relation. If you want to understand a question, you need to know what gave rise to it. And so what I want here is I want you for each of these questions to understand what gave rise to it in the first place. Second, why it became so important by 1642. And third, why it was a resisting straightforward answer, any kind of resolution. If you understand that for these 6 questions, you've gotten everything you need to get out of the first 5 weeks of this course in terms of preparing for Newton. Because, of course, Newton understood just where these questions came from, why they were proving difficult, why they were important, and he addresses all of them. All these 6, he doesn't successfully address the one about distance, but all of the others he's quite preoccupied with. So that's the point. You don't have to know everything about astronomy. How much you choose to learn about astronomy is up to you. But I do want you to appreciate that these 5 questions were really very much at the forefront by 1642. They don't go away over the next 42 years, as you'll see. If anything, they get more complicated. All of them. Yeah, not one of them really goes away. All right, so for the next 5 weeks, we're going to be doing mechanics, but that requires some explanation. Technically, the way I like to describe it is what we're going to be doing is the mechanics of motion. And I have to distinguish that because the term mechanics was already very much in circulation going quite far back, but it was the mechanics of the balance, the lever, the screw, the pulley, the wedge, and starting with Leonardo da Vinci, the inclined plane, where we think of it as statics, but they thought of it as machines to do things like lifting, making lifting easier, etc. And that science probably goes back before Archimedes, but it gets quite rich with Archimedes. And the only name up there that really made major contributions to statics beside Archimedes is Stevin. He was a little bit older, 20 years older, both born 16 years before Galileo, died 22 years before him. Stevin, in a series of volumes, works out what we think of as statics to just an enormous level of perfection. And because he was Dutch, he had a huge influence on Huygens, who will be the person we're aiming to get to in our 5 weeks in mechanics, because he ends up being the most important person. I have no expectation that Galileo himself read Stevin. Stevin's in Latin, it's accessible. But almost certainly Viviani, who prepared the second edition, the posthumous edition of Two New Sciences, read him, because the diagram that I'll show later to try to justify what Drake calls Galileo's postulate is a diagram right out of Stevin. It's possible Viviani arrived at it separately, but perhaps not. The other Dutch name up there I threw up is Beekman. He's going to show up week after next. He's the person young Descartes worked with and ended up getting some of the same results as Galileo got on motion independently of Galileo in the 1618, 1619 period, when Descartes was quite young. He was 22 or 23 years old, and he linked up with Beekman when he ended up getting out of the German army. I guess it was the German army. People may know his biography, but he was conscripted and working in the military, and as he got out of that, he worked with Beekman for a period. And Beekman was very much doing mechanics of motion. The two medieval figures, well, it's groups, Mertonians, our whole group at Oxford, and Jean Buridan, a fairly major philosopher, and Oresme, famous precisely for his work on motion. They both looked at what we now call, what Galileo called, uniformly accelerated motion. I'll pass around. There is a classic work of translation of works in mechanics in the Middle Ages by Marshall Clagett, one of the principal founders of modern history of science. My copy, as you'll be able to tell, partly from those bookmarks, is Bernard Cohen's copy. I had the good fortune of inheriting whatever books I wanted from Bernard, and this was a book I very much wanted. Oresme is particularly important here because there's no question Galileo he definitely knew Oresme, and Oresme's proof of what's called the mean speed theorem, which Galileo offers himself, and it's essentially the same proof. But we know Oresme was being taught in Padua when Galileo was there. What he knew of the Mertonians, probably not much, and I don't know what he knew of Buridan. The four Italian names, and I'll pass that book around as well because it's a collection of translations of the four of them. They were working largely on mechanics of motion, as a matter of fact, though Da Vinci was more concerned with inclined plane, pushing things up inclined planes than lowering them. But the point in the whole group is that Galileo was not sitting there in isolation. Things were going on around him. Though in his particular case, he does have claim to developing a new science because nobody of those before him on motion came close to developing it to the level he did. That is, calling it a science seems wildly premature for all of the rest of them. They were trying to get to where Galileo got, is probably a better description. But there's stuff in the Italian tradition on projectile motion, probably initiated by the military. Galileo did early work for the military. Military has always been a nice source of funding if you want to do research. And so that was true for some of them. What I do want to do is spend a moment on Archimedes. I've added slides for the first time on Archimedes, principally with the thought that Galileo modeled his work on Archimedes' work, two works in particular, on floating bodies, which is the work that Archimedes is truly legendary for. The fundamental result, any body displaces an amount of water equal to its own weight, etc. But the one I'm going to be showing you is no less important. When I say modeled on, I'm actually consciously using the concept Kuhn introduced originally when he started using the word paradigm, a word he abandoned later in life because he had used it in so many ways he thought the only thing he could do is quit using it. But his original idea, and I'm almost quoting now, is an achievement from the past that you model your work on. And Archimedes is very much an achievement from the past that Galileo modeled his work on. So this is from the Equilibrium of Planes. I've just given you a couple of excerpts. One's very important, the others are not necessarily so important. The three postulates I want to emphasize, equal weights at equal distances are in equilibrium, and equal weights at unequal distances are not in equilibrium, but inclined towards the weight which is at the greater distance. So we don't actually get specifics of motion. We simply say when you're in equilibrium and what happens when you lose equilibrium. You incline in a direction, but no detailed description of motion. Similarly, the second one, if when weights at certain distances are in equilibrium, something be added to one of the weights, they are not in equilibrium, but inclined towards that weight to which the addition was made. And correlatively, if anything be taken away from one of the weights, they are not in equilibrium, but inclined towards the weight from which nothing was taken. I'll let you look at the others, but you'll notice what happens here. You start proving propositions one by one, and you can look at them the same way I want you to be looking at the ones in Galileo, particularly next week. Very often you prove a proposition in order to put you in a position, it's enabling, put you in a position to prove a more important one later. So when you look at these and look at them in order, proposition 1, 2, and 3, if you ask why are 1, 2, and 3 there in the sequence they're in, the best way to answer it is see how they're appealed to later, because that's almost always what's going on. You're building something up. That's true in Euclid, and he's simply mimicking Euclid to a very great extent. The next slide gives, it's the classic reference for what's called the principle of the lever. You won't quite see it as the principle of the lever, but let's read. I'm not going to go through the proofs. I'm simply going to do the proposition itself. Two magnitudes, whether commensurable or incommensurable, I'll come right back to that, but notice two different propositions, balance at distances reciprocally proportional to the magnitudes. So if you know the bodies you have, and you want to lift one of them, you first set this up reciprocally by the distance, and then you add weight to the one you don't want to lift in order to lift the other one. Okay, is in effect what you do here. And that's the principle of the lever, and it's important for many different reasons. One of the most important in this course is in I guess it's the 11th week next semester. We're going to see Johann Bernoulli announcing in print 3 years after Newton died, Newton doesn't understand the principle of the lever, which is correct. He certainly understood the principle of the lever, but he didn't. Anywhere we've got rotational motion, he gets confused between forces and torques. He doesn't understand what a torque is, what we now call a torque is, and it's fairly striking. And Bernoulli's not wrong in saying that. The conclusion Bernoulli draws, the vortex theory of planetary motion, can therefore be completely defended, and his paper won a prize for that. That's wrong, but he's certainly going to appeal to the fact that Newton doesn't appreciate rotational motion in the way that's needed here. The other comment to make here, commensurable versus incommensurable. This is important. It's going to come up again. So I need to make sure you know exactly what it means for two magnitudes, and we're talking here geometric magnitudes. The term magnitude is being used quite consciously. They're not numbers. Two magnitudes are commensurable if there is a third magnitude that goes into each of them an integral number of times, any third magnitude. And to be incommensurable is then to deny that there is any magnitude that goes into both of the other two an integer number of times. And of course they had discovered that, for example, the hypotenuse of an isosceles right triangle, which its length is by our standards the square root of 2 if the sides are 1, that the hypotenuse of an isosceles right triangle is incommensurate with the sides. There is no length that will go an integral number of times into both. And to go an integral number of times gets translated in Euclid as measure. To measure something is to, in effect, take off some length an integral number of times. Fair enough? And the oddity here is he proves it both ways. He feels the need to prove it, both for commensurable and incommensurable. Why? Because for the commensurable case, it's relatively straightforward to set up the ratios and do the proof. For the other case, he actually has to add some weight to reduce it to a commensurable case. That's the way he ends up proving it. So you can read those proofs for yourselves, but what you're looking at here is something Galileo knew very well. This was published, memory serves me right, it was published in Latin off the printing press in 1567, but it's around that time. It's when Galileo was very young, or just before he was young. It may have been 1547. I'm flipping between the two dates.
Is it the Comandino translation that you're referring to?
I don't know. All I know is it was definitely, I'm looking at Heath and seeing what he's working from. And I'll pass Heath's book. We're now getting new translations out of, for all of Archimedes' work. including by a colleague of mine at Stanford, at least I think of him as a colleague, Evel Netz, is doing translations, but he hasn't gotten to any of the ones on mechanics yet, and we hope he lives long enough to do them all. But that's work being redone with great care at the present moment. At any rate, you have the two proofs, and then you go right into center of gravities, starting with the center of gravity of a rectangle, but this is again one of these places where he's building up to more and more complicated shapes by starting with simple shapes and having them enable proofs of later shapes. So that's the model on which Galileo was working, and he knew very well and pretty much assumed everybody else knew it well. And certainly the principle of the lever, which comes into play very big time in 1691 by Johann Bernoulli's brother, older brother, Jakob Bernoulli, in solving a particular problem that you'll get to know when we get to Huygens. It becomes a central development in modern mechanics, the turning of the principle of the lever into a means of handling rotational motion in conjunction with translational motion is a very big deal. That's, by the way, why Bernoulli says Newton doesn't understand it, because Newton doesn't seem to understand rotational motion. The two places he should understand it, he says very silly things. All right, that is background. Let me get on to the main subject. So 1638 is when Two New Sciences came out, and I want to compare and contrast, as of 1638, where things stood in the motion, in celestial motion versus motion near the surface of the Earth. So what I'm saying here is that in both cases, what is desired, and I'm trying to say this in as neuter a form as I possibly can. In both cases, we want a mathematical representation specifying the location of a body versus time along a trajectory known or unknown. When it's vertical fall, we know the trajectory. When it's on an inclined plane, we know the trajectory. When it's a pendulum, we know the trajectory. But for the projectile motion, the trajectory was unknown, and of course, the trajectory in the celestial cases was very much unknown. But they're sort of doing the same thing, trying to get a geometric representation of motion that locates the body versus time. But look at this difference. If we take 1638, and the point I made maybe too quickly last time, it's one of the reasons I decided to add this slide this time, and I'll just read this out. You adopt Kepler's proposed horizontal parallax of 1 minute of arc, which he had proposed but not himself adopted. That led Horrocks to reduce the eccentricity of the Earth-Sun orbit from 0.018 to 0.0173. Still in error, it should be 0168, but that's because of atmospheric refraction corrections were wrong. And that in turn had led to an increase in the eccentricity of Venus's orbit from 0.00692 to 0.00750. Notice that's an increase really in the fourth significant figure, virtually so. And in the length of the semi-major axis from 0.74413 to 0.7233. That change in the major axis, that's astronomical units, mean distance of the sun from the Earth, that revision then eliminated a 0.11, a tenth of a percent error in the 3/2 power relation between mean distance and period, the second largest of any of the discrepancies. Only Saturn was larger, and Saturn was very much, as Corey pointed out, it had not, to me on Friday, it had not gone around once during Tycho's period of observation. So Saturn could be handled separately. That, of course, is why Horrocks turned to Saturn right after he did Venus. Okay, that was the natural place to turn next if he's focusing on the 3/2 power rule. But based on that based on the removal of that error, he decided that Kepler's 3/2 power rule should be taken to be exact, and that allowed him to tack on one more significant figure to the distance, 0.72333, 3/3. That did not come from observation, that came from the 3/2 power rule. And when he put all those revisions in, he reduced discrepancies in the Rudolphine tables from 5 minutes of arc down to 2 minutes of arc. That's the state at that time of what was being done on celestial motion. We're fussing over reducing 5-minute of arc errors down to 2-minute of arc errors by doing refinements in the 4th and 5th significant figure. Okay. Now, people didn't realize Horrocks had done that till the 1660s, but the point is that was an appropriate thing for him to be doing at that juncture. You know, the Rudolphine tables were there. The crucial issue is what are the discrepancies that they're exhibiting versus observation telling us. And the natural first step is not to assume there's something fundamentally wrong, but instead start looking at the parameters and see if that doesn't remove them. And that's still what we do in astronomy to a very great extent. Now contrast that to the situation Galileo was in. The sole natural local motion that is near the surface of the Earth, that's what the word local means here, is vertical fall. Galileo had originally concluded that bodies have a characteristic natural constant speed of descent that depends on their density and the density of the medium. We call that now the terminal velocity of a body falling in a medium. You never really quite reach the terminal velocity, but any heavy object gets within a smidgen of less than 1% of it very, very quickly, and then continues to fall that way. So you know some of these things. If you fall out of an airplane and you spread your arms and you don't have a parachute, you'll hit the ground at about 140 miles per hour, and that is the terminal velocity for a shape of a human being going down, spreading his arms, etc. Why do I know those? That's because I just work on airplanes. But now Galileo, by the way, that describes nature, that idea. There's a terminal velocity, and objects seem to fall more or less at that characteristic velocity, and it depends primarily on their density and the density of the medium. And it's very Archimedean if you think about it. Archimedes says in the floating body on bodies floating in water that if the density is greater than water, the body falls. He doesn't say how it falls, but it becomes very natural to conclude that it falls at a terminal velocity. Now he was instead proposing that in the absence of any resisting medium, all bodies are uniformly accelerated as they descend. The rate at which they gain speed is the same for all bodies, regardless of their weight and shape. And any observed departure from these results, results from an effect induced by the motion, and hence a second-order consequence of it, namely a resistance that's caused by the velocity relative to the medium as it moves through. So if the medium is moving with the body, there is no resistance at all. Now, that's a totally different picture. And he's at a point, he's worked this out earlier, but he's publishing for the first time a view of what nature tells us happens. We should not think that way. We should instead consider what happens in the absence of air resistance and make claims about that, with air resistance or water resistance if it's falling in water being a second order effect that should be considered separately. Now, these are essentially qualitative claims. They're quasi-quantitative, but we're not talking about differences in agreement that are running in the 3rd and 4th significant figures. It's a different world. To go back to Leon's challenge to me 2 or 3 weeks ago, in this case, we actually have some grounds for saying he's at an early stage of a new science, starting a new science. Okay, and even though there was a rich tradition beforehand, nobody had ever worked out the theory he's proposing here. They'd never really worked out the first theory either, because they didn't have exponentials, and that's what you need to do terminal velocities, etc. You will see it worked out, it's in the Principia quite straightforwardly. But in Newton's Principia. All right, so we're talking about very, very different states of affairs in the two fields, and what we're going to watch for the next 5 weeks, it will culminate in the mid-1670s, 1673 primarily, in Huygens publishing a book that would have been the most important book published in the 17th century on the subject of physics, had it not been for Newton's Principia 14 years later. So that's where we're going. We're building up to Huygens in the mid-1670s and finally getting to more or less the same point that Horrocks is doing. By the time we get to Huygens, he's working to 4 significant figures on the what we would call the acceleration of gravity. He's got that measured to 4 significant figures. So, there's going to be a similar culmination by the mid-1670s, 40 years later, building off of Galileo, but with various people intervening. Any questions about that? If not, I'm going to now jump into 2 new sciences, which is going to take me into some complicated matters. Yeah, go ahead.
Could you just say again where Galileo, I guess I just missed where Galileo is differing from the previous, is it that he's working with?
He's not trying to get anything like exact agreement. That's another world. Even the comparisons to what you observe are so limited.
No, I mean, with regards to like his difference between Archimedes and what he's doing, is it because he's ignoring air?
What he ends up saying is a science of air resistance is impossible. That you'll read next week. And so we should just not even try to get it. We should instead focus entirely on motion in the absence of any resisting medium, and go accordingly. By the way, he's not altogether wrong about that. If somebody designs an airplane, they cannot, with sufficient accuracy, calculate the resistance forces on it. So they build a small model and put it in a wind tunnel to find those. And here is the principle as of 1985. This is almost a quote. I'll give you the statement, then I'll give you the quote. Looking at 6 previous airplanes, 1 out of 2 that test fully adequately in a wind tunnel when you build them full scale, that is, you spend $10 million to build a prototype, is not economically flyable because the resistance is too high. And now the statement in the paper that makes that point of many pages, all we want from computational fluid dynamics is tell us which one not to build. Okay. So in a certain sense, we don't have a science of resisting media. That's why we rely on wind tunnels and so-called computational fluid dynamics. But that's secondary. Galileo didn't really know that. What he correctly said, too many variables are involved. And you'll read that for next week. But think about it for a moment. If you're going to do a science in the absence of any resisting media, you have an obvious problem. How do you test it? Right? So what's the empirical basis for this going to be if we are in a world where there are resisting media and the behavior of objects in resisting media is exactly what he had held to at an earlier point? Namely, what we now call a terminal velocity, a characteristic velocity. So it's a radical step. Previous people had made the step to a point because they were looking at uniform motion and uniformly accelerated motion. But the out-and-out statement of remove the medium, which was controversial whether vacuums were possible at all, remove the medium from consideration, that's a very radical step.
Okay, thank you.
And we'll keep coming back to that. All right, that's the title page of the original. There are a lot of interesting things in it. Notice it's discourse and demonstrations, mathematical demonstrations, pertaining to 2 new sciences. I'll come back to the word scienza. Now pertaining to mechanics and local movement by Senior Galileo, etc., member of the Lincean Academy, philosopher and mathematician of the Serene Grand Duke of Tuscany, with an appendix on centers of gravity of solids. Archimedes' tie, again, to the center of gravity. The tree, I don't know anything about offhand. And in Leiden. Leiden, for those who don't know, is a city outside Amsterdam, by train about a half hour, 20 minutes. It's the city that Descartes would live in, move into anytime one of his works was being published, because they were all published in Leiden, and he supervised the publication. It's the city that Huygens went to college in, the University of Leiden being a great university, and where Huygens' papers are located. And you'll also notice, by the way, it's Elsevier. I've never checked to see if Elsevier has continued. Elsevier is still in Leiden.
That tree is the corporate logo.
And still, oh yeah, but did they discontinue and resume, or has it been one continuous? One continuous. Okay, so it's a publisher still publishing major scientific works, as a matter of fact. Go ahead.
So would detractors of Galileo have said that the claim to being mathematical demonstrations is a reach here, or is because it seems like a lot of his demonstrations are conceptual, as opposed to
Not the proofs of propositions. I've only given you a handful of propositions.
Okay.
He's intending those to be mathematically rigorous. When he gives let me comment this way. There are two things going on here. The book is in a combination of Italian and Latin. It's a dialogue with our same three people, Salviati, Segreto, and Simplicio. Simplicio, however, is not, he's not portrayed in nearly the stick-figured dumb scholastic that he is in the dialogue. He's instead a useful Aristotelian, asking very good questions and sometimes making critical, really crucial points. So that element of polemics is gone from this. But what they're doing is reading a work in Latin by an academician, presumably Galileo, since there are a whole lot of other academicians from the Lyncian Academy around, and they're discussing the books. So the discussions are not mathematical proofs. Everything in Latin is being portrayed as a mathematical proof or a scholium commenting on a mathematical proof. And Stillman Drake has done us the wonderful favor that everything that's in Latin is translated in italics, and everything that's in Italian is not. Okay, I don't own a copy of the original of this. I own a copy of the dialogue because Paolo Galuzzi gave it to me as a present. When I said I don't own a copy, I should have expanded my horizons. But I can buy one in Italy, but I have not. There are interesting questions in it. The other tricky thing that needs to be said here, he was forbidden to publish anything. Okay, so somehow, and we're not sure how, his manuscript was secreted out of Florence, carried in the 1637 period as he's going blind to Leiden, where it is published. I'm not even sure who's responsible. Marin Mersenne has a copy of it very, very early on, multiple copies of it, because he sent one to Descartes for Descartes to comment on. You'll read that in 2 weeks. Descartes does not like this book much, but for interesting reasons. But how he managed to violate his house arrest and restrictions and get the manuscript out and get it all taken care of, I don't know. At one point, I was pretty sure Mersenne had a very large hand in it. Mersenne is the one responsible for Descartes, all of Descartes' publications, setting it up in Leiden, etc. So it could have been, but I just don't know. Do you know by any chance where? But it was in violation. Okay, he was doing something that he could conceivably be given a hard time over. Table of contents. As Stillman Drake says, the table of contents was actually prepared by Elsevier, but it's 4 days and then an added day on the force of percussion. That's one of the many nice things about the Stillman Drake translation that isn't true of the other. There are 3 English translations. One was done in Newton's time by Salisbury, but almost all copies burned in the Great London Fire. And the best we can tell, and we here includes me in this case, Newton never saw 2 new sciences. That makes a lot of people mad when I say that, but what Bernard did was to find out when the library at Cambridge first had a copy of 2 new sciences, 1745, which unfortunately is 18 years after Newton died. So he definitely didn't see it that way. And there's no sign of any copy in Cambridge before that, and it's not clear that Salisbury copies were present in London because so many of them burned in the fire. Okay, for those who don't know, in 1666, 67, somebody help me, I can't quite get the date. There was a massive fire in London, which was a great blessing because it ended the plague. It killed all the bloody rats, the fire did. But the area known as Covent Garden, all of that just totally burned down, and that's where the books were. And then there's a translation that's available originally in Dover Press, now in Prometheus Press, by two people, both with Italian names. I don't remember. It's not a terrible translation. It's not nearly as good as Stillman Drake's. And Stillman Drake has the advantage of the footnotes, the glossary that I did remind people of after John Scott reminded me that I should have reminded people, etc. So the first 2 days are primarily about strength of materials, and the next 2 days are about motion. Notice that we're only going to look at primarily at day 3 and day 4. So the first one's called Second New Science of Local Motions in Uniform and Naturally Accelerated, and then Violent Motion of Projectiles. The distinction between violent and natural motion is, of course, Aristotle. Violent motion is something that requires a force to initiate by dropping an object. I need to have good objects to drop here. So my dropping an object, the motion itself, unless I throw it, is considered natural motion. There is a third category, of course, constrained motion, and it shows up first with inclined planes, and then when Galileo identifies, legend has it, watching the chandeliers in church swing back and forth in the wind, came to realize what we now call pendulums were an interesting physical phenomenon. That is Galileo, who seems to be the first to have picked that up. Okay, new sciences. Let's start with the word scientia or scienza. The term used normally even in the philosophical transactions of the Royal Society is engaged in natural philosophy. It's part of their name. And that, of course, comes out of scholastic philosophy, coming out of Aristotle. In Aristotle, the word physics just means nature. And so natural philosophy is the philosophy of nature, and that's what it meant all through the scholastic period. And scientia, by contrast, geometry is a science. Sciences have a character of being absolutely secure knowledge, not being dominated by conjecture, or even having conjecture as a major element of it. And of course, natural philosophy tended to have a large element in it. There was a development at one time of, particularly among historians, to not want to use the word science because it's a 20th century word. The word scientist was invented, for those who don't know this, it's a wonderful story, by a philosopher, William Ewell, describing a book written by a woman, Mary Somerville, and the point he was making was that she has as much claim to being a scientist as anybody else does because the book didn't. It's a fantastic book, you'll see it later. But you know, the word scientist didn't exist before the late 1830s at all. The word scientia very much existed, and the question is what to make of it. Probably not what we call science, but something significantly more demanding than what we call science. Newton, at one point, you'll see, actually says if geometers would pay attention to nature and natural philosophers would pay attention to geometry, we might finally have a natural science founded on the greatest evidence. And the word is scientia, and he's openly contrasting it to natural philosophy. So it's a loaded word. As I said, historians at one point wanted to use natural philosophy, and I, as head of the Dibner Institute, at a meeting where people were saying we should never use the word science, I couldn't resist saying, so we should call Galileo's book Two New Natural Philosophies, and we should call the French Academy the Royal Academy of Natural Philosophy, which it isn't. You know, the word was being used consciously at the time on scientia, as a very serious word, not the way we use the word science, which is much more lax. I've put in here, for my purposes now, this is my definition of a theory. It is meant to connect with every use of the word theory in classical astronomy. So here's the definition. An interconnected system of mathematical propositions linking measurable parameters to one another into observable phenomena, from which, with appropriate additional empirical information, values of the parameters, for example, one can derive answers to a wide range of questions, including predictive and counterfactual questions. questions about where would Mars be if it had started at such and such a time rather than, had last been at aphelion at such and such a time rather than when it was. Any number of counterfactual questions, any number of predictive questions, any number of questions about if you change the eccentricity of Mars, what difference is it going to make to the orbits, etc. And as I say, the word theory was used by Ptolemy and subsequently by astronomy to refer to just such a framework for the individual planets. Go ahead.
Since this is your definition, how does it differ from a working hypothesis?
Well, notice it's an interconnected system of mathematical propositions. Working hypothesis may not give you any relation among parameters, much less one highly interconnected that lets you answer a whole range of questions.
But it might, right?
It might.
Okay.
I'm not ruling that out. For those who know, this is a definition adapted somewhat from Duhem, but I'm intentionally trying not to use Duhem's phrasing. And the primary influence on it is Sylvan Bromberger, because it's Sylvan Bromberger who talks about question answering devices. But again, I'm trying to describe what we've talked about so far, because now we're going to be looking at what it is to develop theories of strength of materials and local motion. Okay, and what I mean here is a system of mathematical propositions, but the important thing is the parameters linking to one another. Okay, with that said, let's take the Apollonian parameters. I'm not going to run through these. These were all identified before Apollonius, but by the time of Apollonius, they had been singled out as the relevant parameters for doing orbital research. And if you think about it for a moment, none of them are straightforward things that you just look at and see. That is, they're not parameters that are part of natural language. They're concocted parameters, concocted in every case in an effort to describe something you're observing in a way that has regularities to it that are absent under other descriptions. So the very act of trying to form a theory means you've got to discover these parameters. They don't come for free, and it can be very, very difficult to do. Ptolemy had the great advantage that he inherited all of these from the Apollonian period. And then as I comment here, the italics, each of these was linked to specific observable phenomena, many of them to the same phenomenon that Ptolemy used. They were each measurable. They were each assigned a physical significance, but the great thing is that physical significance kept changing through the ages. So when we get to Copernicus, they have a different physical significance, etc. But it's the parameters themselves that are enabling you to do the theory. Now the issue is, these are the good parameters, now I have to find the relations among them. But look, it can't be that way because you're simultaneously discovering the parameters and getting robust relations between them. The two have to go together. In fact, that's the hard part in general of constructing theories, is the two have to go together. Fair enough? And I'm going to illustrate that now with Galileo's first of two new sciences, strength of materials. So the question is, it's beams. He's only interested in beams, and he's hanging weight on them. And the question he wants to answer is what parameters govern fracture. If he can get the parameters, then he can start predicting fracture and do counterfactual, etc. Well, it's obviously some combination of the dimensions of the beam and the applied load, the weight. But fine, what combination? His attempts at strength of materials got very little of anywhere. And when you look at it and look retrospectively, big time retrospectively, he didn't have the right parameters. The first right parameter is stress. Stress and strain, of course, but stress. That emerges in the 1820s, that we finally get stress as a generalization of pressure. Shear stresses were discovered by Coulomb, but the general notion of stress finally emerges as elasticity theory and continuum mechanics is worked out by a group of people in the 1820s, all in France. Poisson, Kochi, Saint Venant, and Navier being principal names of that. What might interest you, and this of course is my engineering field, stress is a very mediocre predictor of fracture. If you depend on stress for fracture, well, I'll do it this way. If I go out and measure the stress at which specimens fracture, the spread in the data will surprise you. In fact, I'll tell the story about myself. I was a young engineer working on a very, very advanced project and went to metallurgists trying to define what a lower safety margin would be because we were ready to run a lower safety margin. And I said, I want to see the actual data that this design curve of allowable stress is based on. And he showed me the data, and I remember I was 19 years old. I said, you got to be kidding. The data had a huge spread to them. It was very discouraging. Well, in the 1920s, a man whose name I didn't recall and I didn't have a chance to look it up, he became the chief designer of jet engines at Rolls-Royce, 20 years, Griffiths. That's the name, Griffin or Griffith, one of those two. Discovered a new parameter called stress intensity. And that's the one that tends actually to govern real fracture. He discovered it for brittle fracture like of glass, but it applies pretty much across the board. The principle's the following. Almost any real object, real metal, etc., have small defects in it. The question now is what stress level is needed for that defect to become an unstable crack and propagate at the speed of sound. I hope none of you have ever heard a crack propagate at the speed of sound. If you have, it's very scary. It's quite loud and quite scary. I have photographs, if you want to see, of an airplane where that happened and a part of the fuselage came off. Fortunately, only one person died in the process, but the crack was quite audible to all the passengers sitting there. So at any rate, stress intensity is, to tell you how strange it is, I'm sure nobody here has heard it unless they've been trained as a mechanical engineer. It has the following units. Units of stress times the square root of distance. That is pounds per square inch times square root of inches in English units. And it essentially correlates with energy. In fact, I can say what it is. When an infinitesimal increase in the defect releases enough strain energy to keep the defect growing, then it takes off. It becomes unstable and takes off. And that's what stress intensity measures. So Galileo had no way of getting near that if it took another 100 years after we had stress identified and all the theory of elasticity to come up with it. I'll do this one last way. If you go to any engineering textbook on failure, on cracking, formation of fracture is the right word, you will find that there are 5 standard criteria for fracture, and they don't agree with one another, and the field cannot agree on which one's appropriate. Okay, so Galileo didn't have much of a chance of getting anything. Now, Isaac, you wanted to ask?
Oh, no, just trying to call.
All right. It's a strange unit. Very interesting unit because it turns out to be extraordinarily important. And almost all fracture in the real world is tied to stress intensity. What is called, by the way, is fracture toughness. A material has higher and higher fracture toughness the greater the stress intensity it can withstand, which means the larger defect it can withstand for a given level. That's what you like. You like things not to crack, okay? All right, so what are his parameters, Galileo's parameters for local motion? Well, this is fairly striking. What we're talking about as local motion here is uniform motion, naturally accelerated motion, both free and constrained, and violent projectile motion. That's what we're going to be studying. And he says, in the absence of resisting media, that's a key phrase here, the only relevant parameters are distance, height of descent or ascent, time, and speed. In particular, the weight of a body does not matter. The shape of a body does not matter. All bodies behave in exactly the same way. It's an extraordinary claim. So irrelevant parameters in the absence of a resisting medium, weight, shape, density of the body, density of the resisting medium. The very parameters that show up most prominently if a resistance force is present. disappear entirely when you drop the resistance and you go to the initial ones. Okay, now that's a fairly radical idea. What's radical here is not the ones at the top, other than singling out the height of descent or ascent. But time, speed, and distance are not radical. But the claim that none of these others, all these others can be ignored, flies in the face of everything you see around you all the time. And it is a quite radical proposal, going back to this question Leon asked. He's doing something quite extraordinary. Question? Okay. What's his basis for separating those? Well, there's this famous thought experiment that gets repeated in the Discorsi about weight. I'll just, it's in the dialogue as well, and I can't remember whether I assigned that part of the dialogue. It's quoted so often. So here is a rectangular slab and it's falling. Now you put another body on top of it. You're going to make it fall faster? Well, if that's right, if you put another body below it, it's going to resist the motion, right? The smaller body, because it falls slower and it's going to resist. Now, the thought experiment is the little body on top or the bottom makes no bloody difference, and therefore the weight doesn't make any difference. That's a thought experiment. He gives other thought experiments. That's the one I single out on page 108. Then there's the claim he of course is famous for dropping objects from the Tower of Pisa. It's one of those things he's famous for that he surely never did and never anywhere claims to have done it. Okay, so this is one of these that's like Newton's apple. It's taking something. It appears that people did drop objects off the Leaning Tower of Pisa. And he might have even been present when somebody did it, some sort of an experiment, but there's no claim by him that he did it. But what he does claim is that if you take bodies of different weight, the heavier does invariably land sooner than the lighter, but not proportional to the weight as Aristotle requires. As Aristotle says the time is proportional to the weight. Then his third basis for the claim is the effects of resistance on a falling body are smaller the less density of the medium. So you start in water, the effects are very large. The effects can be large enough that it sits on the top buoyantly. But if it's falling, the effects are much more dramatic than the same object in the air. And now he argues, take that to the limit of no resisting medium, and weight's going to disappear. And then there's the fourth, the two brachia pendulums, one with a cork bob, the other with a lead bob, remain synchronous with equal periods, even though resistance affects the former more. And I'm going to deal with that in a moment. I want to pause with this because I want you to realize that at this moment, the moment he says these are the parameters that count and these are the parameters that do not, a very large part of the exercise has been completed. So the basis for claiming that has to be empirical in one way or another. It can't be mathematical. That's why it's not presented mathematically as part of the academician's treatise, but has to be argued for quite separately. And then there's a question whether these arguments are really adequate. Okay, and I will raise questions about that. I want to say one other thing before we go on. Speed for him is not our notion. The word he uses is velocitas, in Latin. I didn't bother to look at the Italian, but I know what it is in Latin. It is not a vector quantity. And just to try to drive that point home, Cameron will laugh at this. Vector quantities came into existence around 1900, before or after. They were invented by Willard Gibbs as a teaching device at Yale, trying to make electromagnetism easier to do than it had been without them. And you agree, it's easier to do. He's been writing about Maxwell without them, and it's not easy. And when the book got published, one of his students named Wilson intervened and said, can I write these up, my notes up, and we publish a book on what became vector analysis. And the first 4 pages are going in great detail, making the following point. And I won't do it here, but you can picture it. Suppose I draw 2 equal length arrows on the blackboard, parallel to one another. Question, how many vectors have I put on the blackboard? And the point is 1. Vectors are quantities. It's like writing the numeral 2 up there. How many numbers have I put up? That's a very difficult concept. That's why it didn't show up to 1900. That's way after physics became extraordinarily rich and complicated. We finally get the concept of a vector. Okay, so needless to say, he's very far removed from that. That's not a trivial notion. But on top of it, more peculiar from our point of view, he doesn't think of it as an extensive quantity. Length, time, etc., those are extensive quantities. The heat, the hotness of a body, what we would now call temperature, they didn't have a way of measuring temperature, but the heat of a body, the solidity of a body, those are intensive properties of a body. And he thought of speed as an intensive property of a body, something a body acquires as a property that allows it, when it impacts something, to do more and less damage. And associated with the notion of speed, as this he inherited from the Middle Ages, the word impetus, which are little increments of adding speed to a given mass, giving it added capability of doing damage when it hits something, as in a ballistically. Or his favorite word, memento. My friend Paolo Galuzzi, whose name I've dropped 2 or 3 times from the IMSS, his first book was a 600-some page book on the meaning of memento in Galileo. And that will give you a sense of how elusive that concept really is. It's obviously related to our notion of momentum, but it's not it. Okay, he's just thinking in a totally different way about these things, particularly thinking intensively, which leads me to make the point I want to make about this before I go on to start looking in more detail. There used to be a course at Princeton taught by Tom Kuhn. For many years, when he taught it at MIT, I co-taught it with him because I did the Newton portion. But what he would do was start back with Aristotle on motion. For those who don't know, Aristotle doesn't really distinguish motion. He distinguishes kinesis. Kinesis is any form of change, and he has a general theory of change and treats motion as simply a species of all other forms of change, which means motion doesn't look like we think of it at all. And what Kuhn would do is show the history from Aristotle down to Newton of how our concept of speed, the relevant concepts tied to motion, evolved during that time. And the point he was making time and again, and this is Kuhn's picture of science, what science is all about is forming a vocabulary that lets you conceptualize the world around you in a coherent way. And you can do that in multiple ways. Aristotle was perfectly coherent, but he didn't do the things that were done later. Increasingly, you get to a point where you can solve certain kinds of problems with your reconceptualization. But the emphasis all the way through, and it's a twofold emphasis, I'm telling you about this because I'm going to make the key point here. The emphasis all the way through that course was teaching students to read their way into the conceptualization that people had who wrote the books. And the real thrust of that course, which used to be taught to a large number of undergraduates, is you have to stop looking at things retrospectively if you're going to understand these things. Okay, and then, there are funny things about the way he taught Galileo. I'll mention it later. But the point I'm making, that's one reason I'm having you read it and pay attention to it, because they really are thinking about speed, motion, etc. in very different ways from us. And to really understand what he's doing is going to take some effort. I'll get to that in a moment. But ultimately, this, particularly about motion, it is changing very rapidly during this century. So by the time we get to Newton, we have something that looks an awful lot more like what we think of as motion. Not the same, but much, much closer. Fair enough? I mean, that's why this stuff about parameters is important. You remember what I said about Apollonian parameters? The same parameters get reinterpreted time again. Well, that's what happens with Galileo. The same parameters get reformed into ours and you don't even notice that you're doing violation to the text. What Kuhn would teach you to do is show you that the way you're reading the text has fierce anomalies in it. Then he would say, and you think those anomalies are because the person didn't understand, and then gradually make you realize what he had gone through to begin with when he first got into history of science, learning to read Aristotle when it was coherent. He was teaching that all over again to students. I'm not going to be teaching that, but I'm going to spend the next roughly 20 minutes or so on the conceptualization and then start looking at questions of evidence. Okay, maybe a half hour on conceptualization. But do hear me, they're not our concepts. I'll write algebraic expressions up there like s equals 1/2 at squared, and I'm totally being anachronistic, other than I can interpret each of those in his terms, but they're just not ours. Okay? I can't say that too often. Now, on his claim about the pendulums, this is rather distressing. I'm just going to read the whole passage out because it's so striking. So I fell to thinking how one might many times repeat descents from small heights and accumulate many of those minimal differences of time that might intervene between the arrival of a heavy body at the terminus and that of the light one, so that added together in this way they would make up a time not only observable but easily observable. Problem is, when you drop objects from a small height, it's difficult to get a measure of how different in time they land. Ultimately, it's a small skip, you can see where it is. Ultimately, I took two balls, one of lead and one of cork, the former being at least 100 times as heavy as the latter, and I attached them to equal thin strings 4 or 5 brachia long. Brachia is a forearm, roughly 2 feet, so we're talking here 8 to 10 feet long, tied high above. Notice the word pendulum isn't being used here because, it's not quite there yet. Removed from the vertical, these were set going at the same moment, and falling along the circumferences of the circles described by the equal strings that were the radii, they passed the vertical and returned by the same path. Repeating their goings and comings 100 times by themselves, they sensibly showed that the heavy one kept time with the light one so well that not in 100 oscillations nor in 1,000 does it go ahead in time even by a moment, but the two travel with equal pace. The operation of the medium is also perceived, offering some impediment to the motion. It diminishes the oscillations of the cork much more than those of the lead, but it does not make them more frequent or less so. Indeed, when the arcs passed by the cork were not much more than 5 or 6 degrees, you can picture it slowing down from the resistance effect, and those of the lead were 50 or 60, they were passed over in the same times. That's the claim. And he sure seems to be describing a real experiment, doesn't he? But you do that experiment, there's no way they stay remotely in synchrony with one another. Okay, I just want to pick out one thing, then come back to the main point. Do notice he knew, and everyone knew really, the heavier an object, the less the effect on resistance. Okay, so that's in there. The sequence here is, this is first described in a letter of 1602 to one of his mentors at Pisa. I have to look up the name, it's not a name I know immediately. Dal Monte. Then he makes a slightly less detailed, well, significantly less detailed statement in the dialogue, but he certainly suggests that the time of any pendulum is independent of the arc length of a circular pendulum. And it's just flat false. When I told my daughter, the telescope daughter, the daughter who loved Galileo, when I told him, well, I said initially, because I didn't know of the letter from 1602, that he was just lying about doing this experiment, she got very upset with me and made me do the experiment. So we actually reproduced the experiment, and she was very discouraged to see, sure enough, they go out of whack almost immediately, depending on how large of an arc. So what I've actually given you, I've just worked this out, the formula's at the top. You won't see this formula in anything but a very advanced book Nobody in the 17th century or the first half of the 18th century could derive this formula. It involves an elliptical integral. I don't recall whether it was Lagrange or Euler who first actually solved this problem, but whatever it is, it's an infinite series solution. But you can see the number of full cycles before a 20% discrepancy. If you're running 15 degrees, which is not very much, it sure isn't 100 or 1,000. But if you're running 30 degrees, which is the kind of arc he would naturally have done, it's very, very few cycles till they're 20% out of sync. And now the question is, at one point I said he lied. Once I saw the letter, it was actually Nico Bertoloni-Meli finding the letter in the Dibner Institute and showing it to me and say, what do you want to say about this? And I had to say, he clearly did the experiment. The question is, what in the world did he see? And what Bertoloni-Meli says in his book is he probably just described the discrepancy to something like some secondary effect and chose to ignore it. But that's not the description here. It's possible to set things up in synchrony if you link them in the right way. They'll feed one another. And so it could be just a badly designed experiment. We don't have an answer to how he could have thought it was synchronous. Circular arc pendulum were synchronous. The technical term here is isochronous. What path do you reach the bottom in the same time, regardless of how far away from the bottom you start? That's a peculiar concept. You start at 1,000th of an inch away, you start it way up many feet away, you arrive at the bottom in the same time. That became a question out of this, particularly when Mersenne said circular arc pendulums are not isochronous. But he said that, and then Galileo repeats it in Two New Sciences, so we don't know what's going on. But they're not isochronous, and it becomes a major question. It is the question that's the principal question in the book I told you about earlier, Huygens' book of 1673. He solves this problem. It's a very big deal in the history of clockmaking. I trust you can immediately see the virtues of it being isochronous if clockmaking, because as the arc slows down, it doesn't affect the timing. And Galileo proposed it for clocks. They would not have been very good. All right, with that said, let me turn to a different question, now more one of getting at the radical character of his splitting vertical fall into two and motion near the air into two separate mechanisms. That's really what he's doing. He's saying that natural motion and projectile motion really consists of two separate mechanisms. One mechanism is motion in the absence of air resistance, and the second mechanism is induced by that motion in the medium and takes the form of resistance. Okay, and the natural question is, when is it legitimate to say that something that happens in nature is being composed out of two completely separate mechanisms, and we should approach it as composed? And I give three answers here. One is that even to get at the secondary mechanism, you need a full theory of the primary mechanism. And that's Newton's approach to trying to get at resistance forces, is to have such a good account of the primary mechanism that you can then work out what the added effect of air resistance is. That's in the Principia, as you'll see. Then the second is you can get results of evidential value only if you remove the confounding effects of the secondary mechanism, because they are confounding, they're messing things up. So give a theory and then introduce corrections for the secondary effect. I'll give you an example of that. Mercury in a thermometer, there's a cohesive effect, capillary effect on the tube. You really want to design it to make corrections for that, so it doesn't give you a misleading value. I can give you many examples of that. And the third one, which seems to be Galileo's, is no theory of the second mechanism is possible at all. So trying to do the two together is going to prevent you from ever having a theory. The key is to find to separate the two mechanisms and get a totally adequate theory for the principal mechanism, then take care of the secondary mechanism by various approximations, corrections, engineering devices, etc. And I've sort of already told you that's the state we're in a lot of engineering fields, or certainly that's state in strength of materials. I didn't tell you this, by the way. I should have told you just to whet your curiosity. Solid state physics measures the cohesive energy of a solid. It's an order of magnitude greater than the energy needed to fracture it. It's one of the deep mysteries of solid state, deep research problems in solid state physics. Why are real crystals 10 times weaker than solid state physics says they are? It's called, the area is called dislocation theory, but it's essentially a search for an answer. They have not succeeded in getting it. One last thing, just for people's interest. Tom Kuhn's physics doctoral dissertation was on cohesive energies in solid state physics. But that's neither here nor there. So those are the reasons, and it's really Galileo finally tells you in day 4 that his reason for getting rid of air resistance is the third one. Descartes' going to say the same thing. He's going to toss out air resistance as being beyond science, so they're not unique. All right, now we go to uniform motion, and I get to start showing you the way he conceptualized things. So staying within the framework of Eudoxian ratios, where you're supposed to compare similar items, we get ratios, and I'm putting them up here properly. In a given time, two different objects moving, the ratio between their speeds is the ratio of the distances covered in a given time. Now, over a given distance, the ratio of the two speeds is inversely as the ratio of the two times. So it's subscript 2 in the first, subscript 1 in the second. We would, of course, replace these by fractions and think of it as division. And I could do that, and I'll frequently do it in this course because it's so much easier for us to think of it that way. That's not the way they thought of it. They thought of it as ratios. So, therefore, speed in uniform motion varies directly with distance and inversely with elapsed time, the compound of two ratios. The way we would write that is two fractions and multiply them into one another, and of course you would get the ratio of 2 feet per second relationships, two speeds. They thought of it as compound ratio. It's the equivalent of multiplying the two. But what Proposition 6 then announces, and notice it's 6, you had to get there through the earlier steps being the ones at the top that I didn't give proposition numbers to. If two movables are carried in equable motion, the ratio of their speeds will be compounded from the ratio of spaces run through and from the inverse ratio of the times. And he actually gives a proof where he lets, I can't quite see it, but I hope you can look directly at the note. V and T represent the spaces, S and R represent the times, and the ratio of the speeds is represented by the ratio of C to G compounded from the ratio of C to E and the ratio of E to G. So we end up over here on the right of lengths representing the speeds being obtained from lengths representing the times and lengths representing the distances. And that's the right word, represent. We have geometric magnitudes representing 3 different magnitudes. Go ahead.
So this is a different way of thinking about speed and time and velocity, but these aren't different parameters in the way you were talking about how Kuhn wants us to look at different parameters, right? These are still the same things, we're just talking about them differently, right?
We're representing them mathematically in a mathematics that's totally different from the one we would use. We would think of speed as a number. He's not doing that. He's representing speed not by a number, but by a geometric magnitude.
But he's still picking out the same parameters, in terms of earlier we were talking about what.
That's right. It's same parameters. Now what I'm emphasizing now is the way he mathematizes them, which is very much geometrically, using Eudoxian ratios. Okay? But the hard thing for us to overcome is we think of all of these as being represented by numbers. And you multiply the numbers together, I'll come right back, Marius, to get another number. He's not thinking that way. In fact, when he puts numbers in, David Gottlieb asked me this question in an email. When he puts numbers in, he almost always uses things like roughly or approximately, because he doesn't think of numbers as necessarily getting exact magnitudes. Go ahead.
Does it mean average speed or instantaneous speed?
Here it's uniform motion. So it's constant speed. One speed the whole way. And this holds only for that case, of course, his relationship. So what I have now done, and we'll stop when we get to the end of this segment, I think, I've given you 3 pages out of a wonderful website. I had the pleasure at Dibner Institute of being asked to be a referee for this guy's tenure at Clark University, and I already knew the website. And boy, did I pour it on how, and he's still there, he got tenure. But you know, they were complaining he didn't do original things in mathematics. What he did was take all of Euclid's elements, put it into a website. You can't see it here. You actually, in this case, I can't manipulate things. Well, I'll show you in the next curve. But in all the figures, you can change the figure by just moving a spot around, and start appreciating how robust the theorem actually is, because it's not tied to any one figure. I'll show that in just a moment. This happens to be what's called Euclid's algorithm for finding the greatest common divisor of 2 magnitudes. And there happen to be numbers, okay? That's what you're doing. But the numbers, even for Euclid, are represented by lengths, and he then tells you, subtract the one length down until you have a remainder that's too small to subtract anymore. Then take that one and subtract it from the other one, and when you're through with that, you have the greatest common divisor. And you notice he's using the word measure up here. He's presupposing that these 2 are commensurable with one another. The 2 lengths are commensurable. And he's also presupposing they're not prime. I showed you that just because it's, you know, the algorithm named after Euclid. The ones that are interesting are the next 2. The mean proportion. The mean proportion between A and C is the magnitude B such that A is to B as B is to C. If you look at the bottom here, it ends up being x squared corresponds to AB. Now, what did they know about this? They knew the very high likelihood of incommensurability among those lengths because they're dealing with right triangles. Okay. So if they put numbers to them, it may be impossible to specify the exact lengths, because one of the numbers is going to be irrational with no pattern, and the best you can do is approximate it. There's no approximation here. You want the mean proportion between A and B and C. You take AB, you extend it to BC. You take the midpoint of that, you draw a circle. And at point B, the intersection of the 2 lines, you raise the perpendicular. That's the mean proportional. And it's an exact mean proportional between any 2 lengths whatsoever, whether they're commensurate or not. How do you want to get a square root of something geometrically? Square root of 5, I take 5, I add 1 to it to get a length of 6. I draw a circle that's from the midpoint of that, and at the point 5, 1, I raise a perpendicular to the circle. That's the mean proportional. And the thing that makes this mathematics special, and it's one of the reasons Newton uses this very mathematics in the Principia, is all questions of incommensurability and exactness are gone. Geometric magnitudes are exact. That doesn't mean when you draw a circle it's exact. We have all of the classic Plato objections to the drawn figure not being perfect. But we're treating these objects as perfect figures, and in this case, this is the way you get mean proportionals. It's a very, very well-defined quantity geometrically, regardless of what magnitudes you're doing a mean proportional between. Now, the nice thing about this is point D I'm trying to remember which one can be moved here. It's probably point B is, I think, the point that can be moved. You can go on the website and start playing. It's all 3 volumes, all, 10 or 11, 13? I can't remember the number of books in Euclid. Anybody remember? 13? Yeah, it's 13. On, and really learn Euclidean geometry the way it should be learned. now available on that website. It's great fun. The other one I gave you is the third proportional because it's more tricky. A is to B as B is to an unknown. The unknown is the third proportional. In this case, you start off, let's see what he's specifically doing. The third proportional between AB and AC. So what you do is extend the triangle so that it ends up that AB is to AC as AC is to CE. And the construction, again, gives you the exact magnitude that's the third proportional, the missing unknown in those. And we can keep doing this, place after place. We can construct things totally exactly without numbers. That doesn't mean we can't put numbers on them. The point is we have complete exact rigor when we work geometrically. It is not clear it's even possible to have that when we work with numbers because of incommensurability. Again, it's very foreign to you, but how many of you actually had a full year course in Euclidean geometry? Yeah, these people who grew up outside the United States, went to school outside the United States. I'm old enough that I had it. You had it? I'm impressed. In Beverly Hills? Yeah, I'm impressed. Had good teaching. At Lionel's school, Beverly Hills High School? Okay, that private school, that makes a difference. Fair enough. They don't have to go by state rules. At any rate, that's the math. And I'm giving it to you, starting with the reading for tonight, because I've got to get you accustomed to looking at rudimentary Euclidean geometry because that's what's in the Principia. Okay, he will switch to numbers some, he will switch to algebra, he will switch to symbols. But his primary mathematics is geometry, and I gave you the first reason. It's exact, numbers are not. The other reason is he thought you can do limits completely rigorously geometrically, and he didn't think you could do limits completely rigorously working symbolically. And nobody did figure out how to do it until the 19th century. So we'll get to that later. All right, with that as background, let's stop here and take the break now. It's 5 of 8. We'll come back at 5 after 8 and start looking at uniformly accelerated motion. Well, I'll field questions when you come back. That's the easiest thing to do.